Hello, everybody. Welcome to 7.7. So this section is going to be all about geometric sequences as exponential functions. So we briefly talked about this before in some of the earlier work that we did. This time we want to focus on what the sequences are, what they look like, and then we could talk about some pictures that are related to them as well. So geometric means when we have a common multiplier, if you remember. So we're going to be looking for a common multiplier with all of our things. So we call that a geometric sequence when we have a multiply by everything over and over and over again. Whatever we multiply by every time, we call that the common ratio. So here we go. First example, 1a, looks like this. We want to determine whether this sequence is arithmetic, geometric, or neither. So if you recall, arithmetic or arithmetic is going to mean we have a common addition or subtraction. We're adding or subtracting the same value every time. Geometric, on the other hand, is a multiplier. So we're multiplying by the same value over and over again. Neither would mean there is nothing in common at all. So for this first type of problem, we're asked to look at the numbers and see is there any common pattern. So from 0 to 8 to 16 to 24 to 32, is there anything in common that's happening every time? Well, I can see for sure there's no common multiplier. There's nothing you can multiply 0 by that wouldn't be 0. So we'd have to be adding or subtracting something. And if you add 8, you'd get from 0 to 8. If you add 8 again, you'd get to 16, then to 24, then to 32. So it looks to me like we're adding 8 every time. That would make it arithmetic, when you're adding or subtracting the same thing every time. So we see that is true. Every time we go from one term to the next, it's an increase of 8. So if that is true, this is and must be an arithmetic sequence. And the common difference between each consecutive term is 8. So from one to the next, it's always 8 units. And of course, we say it is arithmetic because we are adding 8 every time. So the key difference is arithmetic means add or subtract. We're adding or subtracting some value every time. Geometric is a common multiplier. So for this case, it is arithmetic because we are adding 8 every time. And that is all we have to say for 1a. Adding 8 every time. Okay, so 1b is a totally different sequence to look at. We want to determine whether this one is arithmetic, geometric, or neither. So let's compare the numbers. So to get from 64 to 48 to 36 to 27, is there a common difference or is there a common ratio? So let's think about that. Well, to get from 64 to 48, it looks like I went down by 16. To get from 48 to 36, I went down by 12. And from 36 to 27, we went down 9. So there is not a common difference. But is there a common multiplier? Well, if you want to check that, you can take one term, divide by the previous term, and see what you get. Then take the next term, divide by the previous term, and see what you get. Then check the last term, divide by the term before that, and see if all those fractions are the same. So it turns out 48 over 64 is 3/4. 36 over 48 is also 3/4. And 27 over 36 is still 3/4. So, in other words, if we had 64 to start and we multiply by 3/4, we'd get 48. If we multiplied it again, we get 36. And if we multiplied by 3/4 one more time, we get 27. So the common multiplier is 3/4. That is going to be indicative of a geometric sequence. So this is geometric with a common ratio of 3/4. That is our common multiplier. So this has to be geometric since we're not adding or subtracting, but instead we are multiplying. So all we have to say is geometric, common ratio, 3/4. Great. So with that aside, we can look at one more example 1 type problem. For this one, we need to determine whether the sequence is either arithmetic, geometric, or neither. So let's think about it. If we were to start at 1 and go to 7, we would have to add 6, right? But if we go from 7 to 49, we'd add 42. So there is not a common addition happening here, so it can't be arithmetic. But is there a common multiplier? Well, to get from 1 to 7, you would multiply by 7, right? To get from 1 to 7, you would times by 7. How about 7 to 49? You would times by 7. And 49 to 343, now this you may not know in your head, but it is also times 7. So as we multiply through, we're multiplying by 7 every time. So that's our common multiplier, or our common ratio. So we have a common ratio of 7. So that is going to be indicative of a geometric sequence. That cues us in. We're multiplying by the same thing every time. So it has to be geometric. And that common ratio is 7. So for 1C, looking at our 1, 7, 49, 343 setup, it has to be geometric. We would say letter choice B for 1C. Great. Can we identify? Yes, we can. Those are easy. Now, example 2 type problems ask us to find some terms. So we need to find, in this case, the next 3 terms in this geometric sequence. So we have a common multiplier. So we have to figure out what that is. So to get from 1 to negative 8, what would we multiply by? Well, to get from positive 1 to a negative 8, we'd have to multiply by negative 8, right? To get from negative 8 to positive 64, we'd have to multiply by 8 and also a negative, since it went from negative to positive. So our common multiplier in this case, and you can check this, is a negative 8. We're multiplying by negative 8 every time. So our common, I'll put a C, ratio, an R, is a negative 8. So we're multiplying by negative 8 every time. So we're asked to find the next 3 terms in the sequence. In other words, take the last term, negative 512, multiply by negative 8, and then continue to do that 2 more times. So we already said our common ratio we determined was negative 8. You can check that by dividing one term by the previous term, and you get the same value every time. Negative 8, negative 8, negative 8. So our common ratio is negative 8, that we know. So multiply that by your last term and get the next one. So 512 times negative 8 gives us 4,096. Notice it is positive because our negatives cancel out. Multiply again, you get negative 32,768. And then multiply one more time, you get 262,144. So those 3 represent our last 3 terms for this whole step sequence. So those numbers aside, the general idea is that you multiply by the common ratio, get your next term. For this one, we're asked for the next 3. So it would be 4,096, that's positive. Negative 32,768, that's negative. And then our last one is 262,144, and that is positive, using the same common ratio. Geometric, common ratio, multiply it through, get your next term. Great. So how about 2b? We're asked to find the next 3 terms of this one. So it is geometric, but this one is a little bit different. So we're multiplying, but it is interesting because we're multiplying by something less than 1. So to get from 40 to 20, what do we multiply by? Well, it got smaller, but we multiplied by exactly 1/2. Because 40 times 1/2 gives you 20. 20 to 10 is also times 1/2. And then 10 to 5 is also times 1/2. So it looks to me like we have a common ratio, or a CR, of 1/2. In other words, to get from one term to the next, we must multiply by 1/2. That is our common multiplier. So they're asked to find the next 3 terms in the sequence. So let's do it. If we're at 5, we must then multiply by our common ratio, 1/2. And then we can do that again and do it one more time. So we already know our common ratio is 1/2. We said that. So let us now find the next 3 terms of the sequence. Starting at 40, 20, 10, 5, now find the next 3. So if we multiply through, from 5 times 1/2, we get 5/2. Times 1/2 again, we get 5/4. And if you notice the pattern, times 1/2 one more time, we get 5/8. So 5 times 5/2 times 5/8 gives us all of that. So our last 3 terms, 5/2, 5/4, and 5/8. So we have all of those for our answer for this example 2 problem. Just using our common ratio, continue to multiply, and you notice it divides the denominator by 2 more each time. So 2 to 4 to 8. So that is it. Just follow the pattern, continue to multiply, get your next term. Great. Okay, so these get more interesting. So the nth term of a geometric sequence is given by this equation, which we've already briefly talked about. So any term of a geometric sequence, or a sub n, can be found by taking the first term, a sub 1, times your ratio to the power of the number of terms you care about, take away 1. So let's look at it. They ask us to write an equation for the nth term for the geometric sequence 1, -2, 4, -8. So what is a sub 1? A sub 1 is the first term, which is 1. So we know that is true. That's already given. A sub 1 is 1. Find our common ratio. So what are we dividing or multiplying by every time? So to get from 1 to -2, we'd have to multiply by -2. To get from -2 to +4, we'd have to multiply by -2. And to get from 4 to -8, we'd have to multiply by -2 again. So our common ratio must be -2. We're multiplying by that every time. So we know our ratio, or the r in this equation, is a -2. We already said that. Our first term is 1, so we know what our green term is here. Our blue term is a -2. And our n will depend on what term we care to find. So we can plug in what we know. So first term becomes 1. We got that here. R became -2. We got that here. So our nth term equation then is all of this. Leave the n where it is. Plug in the things you know. Leave everything else. So we get, as an answer for our equation to help us find future terms, a sub n equals 1 times -2 to the power of n minus 1. That is our answer. That is just the equation. So going forward, we can use that equation to find any term we want in the whole sequence going forward. Great. So with that in mind, we can now apply that. So they ask us to find the 12th term of the same sequence. So that is going to be a sub 12. So n, everywhere you see an n, it becomes a 12. N is the number of the term. So 12th term, n becomes 12. So a sub 12 equals 1. All this is the same, times -2 to the power of, now n is 12. So 12 minus 1. Now simplify. 12 minus 1 is 11. So we get 1 times -2 to the 11th. 1 times anything is itself, so we can ignore the 1. -2 to the 11th, you can put that in a calculator, is -2048. So our 12th term will be -2048, because times 1 doesn't change anything. So 12th term has to be, in our sequence, -2048. Done for 3B. Cool. So how about 3C? We want to write an equation for the nth term for this sequence. So we must first understand what is our common ratio. To get from 3 to -12, I'd multiply by 4, but it goes from positive to negative, so it must be a negative 4. To get from negative 12 to positive 48, I'd also multiply by a negative 4. And to get from negative 48 to 192, or from 48 to negative 192, I'd also multiply by a negative 4. So my common ratio is a negative 4. So if that's true, I know that piece of my equation. And I can start to think about what my equation should look like. So we know a sub n will equal a sub 1 times r to the quantity n minus 1. This is our base equation. So our first term is a sub 1. We can plug that in. And our common ratio we also just found. So we're asked to write an equation, so we must plug in those two pieces. So it would look like this. A sub n will be equal to, our first term is 3. Our ratio, we said, was negative 4. So I'm going to put parentheses around it. And then our power stays the same, n minus 1. So this represents our equation to help us find any future terms we want for this multiplying sequence, this geometric sequence. So let's look at the options. B has 1/4 as our multiplier. That's wrong. 1/3 is also wrong. Negative 3 is not right either. So it looks to me like A is done perfectly. This is exactly what we wrote. Has the right multiplier, has the right first term as 3. So A, we confirm for 3C. A sub n, any term, is equal to 3 times the quantity, negative 4 to the power of n minus 1. Great, so let's look at 3D. One more example of this kind of problem. So let's apply the same equation. They ask us now to find the 7th term. So to find the 7th term means when n is 7. So let's take that, use that in our equation to now find what we need. So a sub 7 equals 3 times negative 4 to the power of 7 minus 1. Where did all this come from? Our equation right here that we already said. Everywhere there's an n, it became a 7. So in other words, our 7th term will be equal to 3 times negative 4 to the 6th power. Now from here, you can put all this into a calculator and get what you need. So you know your answer has to be positive right away, since you have an even power. So we should be looking at, and you can check this in a calculator, 12,288. Given that we have negative 4 to the 6th power times 3, gives us this. So that's an easy step. If you have a calculator on your phone or an actual calculator, this will help you. 12,288 for 3D. Great, so if you're keeping up, we have one more example to get through. This example 4 has a little bit of context. We're talking about art. So a 50-pound ice sculpture is melting at a rate in which 80% of its weight remains each hour. In other words, every hour that goes by, we multiply by 4/5. Where did I get 4/5 from? 80% is 80 out of 100. 80 out of 100 reduced to its simplest form, you can get 8 over 10, which is the same thing if you divide it all by 2 as 4 over 5. So we're multiplying by 4/5 every time. Each hour, we multiply by that. If we wanted to draw a graph, we could do it to represent how many pounds of sculpture is left each hour. So the first hour, we have a 50-pound ice sculpture to start when we first have it. And then every hour that goes by, we multiply by 4/5 because it's melting because of the temperature. So if we wrote a graph, you can imagine what it would look like. The number would start out higher, and every hour that goes by would get lower. 80% lower to be exact. So let's see what that would look like. Don't worry about those words. So it would look like this. Now try to generate a picture for yourself. So if you see on the leftmost point, we start up at 50. At time 0, that's when the sculpture is brand new. 1 hour later, it started to melt, and it's melted to reduce to 80% of what it had originally. So if we start at 50, we multiply by 4/5. We would now have 40. And then we go to 32 and keep going down and down and down and down. And each time we multiply that previous value by 4/5. So 4/5 gets us to our next point each time. You can check that in a calculator to get the next value. But you see the general idea is that we have a decay curve here. We're decreasing a little bit every time. This represents our geometric sequence when we have a value that is less than 1. So we're reducing every time. It's getting lower and lower and lower. So that is our graph. Start up at 50, get lower, 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 lower. 6 hours later, you're looking at somewhere around 12 pounds of ice left. So every time we reduce, when our common ratio is less than 1. So here's something you should know as you're jotting down the graph. If your CR, or your common ratio, is less than 1, you're looking at decay. Your graph is getting smaller. If your common ratio is greater than 1, or your CR is bigger than 1, you're looking at growth. Your graph is going to grow really fast. So keep that in mind when you're looking at these. In this case, we had a problem that had a rate of 4/5. So our ratio is less than 1, so we know it should decay, and it should go down, which is exactly what we see here. Our graph is going in the downward direction. So expect to see that as you look at these problems. Growth when your ratio is bigger than 1. Decay when your rate is less than 1. So use all the stuff we talked about to help apply these problems as you look at more geometric sequences.